Before we jump out into the experiment, let me and HANI explain about the magnetic flux. What is magnetic flux? Magnetic flux is a measurement of the total magnetic field which passes through a given area. As we can see over here, we have a representation of a magnetic field. The X mark indicate that the magnetic field are all coming into the screen. The circle frame in this video will be representing the certain area. Now, we can see clearly that there is about 15 magnetic field that pass through the circle frame. So, the flux is the measurement of the number of magnetic field that pass through the circle. So, how can we change the flux?
How about we change the size of the circuit?
Yes, you are right. We can change the flux by reducing the certain area. As you can see over here, I have smaller size of circle frame. We can clearly see that the number of magnetic field that pass through the area has become lower. Thus, the flux also become lower. But, did you guys know that there is another way to change the flux? Let's go back into the larger circle.
Another way is by rotating the coil. When we rotate the coil, we are effectively changing the angle theta. As we rotate the coil from 0 degrees to 90 degrees, the magnetic flux decreases from its maximum value to 0. Conversely, if we rotate it from 90 degrees back to 0 degrees, the magnetic flux increases from 0 to its maximum value.
In this video, we will demonstrate a simple motor experiment that showcases the concept of magnetic flux in action. First, tape the safety pins to the ends of the battery. Next, wrap the wire around the marker to make a coil. Thirdly, loop the ends around to make the coil hold its shape. Next, sand the insulation completely off one end of the wire. Sand only half the insulation off the other end of the wire. Place the wire into the safety pin supports. If it does not spin easily, adjust the shape of the wire. Place the magnet under the coil. And last but not least, give it a push to get it started and watch it go.
Coil and magnet interaction. In a simple motor, the armature rotating coil is placed within the magnetic field of permanent magnets. The interaction between the magnetic field generated by the current carrying coil and the external magnetic field creates a force on the coil. This force is described by the Lorentz force law. The direction of the force is perpendicular to both directions of the current and the magnetic field, leading to a torque on the armature which causes it to rotate. As the armature rotates, the orientation and the area of the coil exposed to the magnetic field change, causing the magnetic flux through the coil to change over time. The forces generated on different segments of the coil create a torque about the motor's axis. This torque is responsible for the rotation of the armature. The continuous supply of current ensures that the armature keeps rotating, converting electrical energy into mechanical energy. During the rotation of the coil, the angle theta between the magnetic field and the normal to the coil surface changes continuously. This results in a time-varying magnetic flux through the coil, even if the magnetic field strength and the area remain constant. According to Faraday's law, the changing magnetic flux induces an electromotive force (EMF) in the coil. The induced EMF drives the electric current in the coil, which interacts with the magnetic field, producing a force that causes the coil to spin. The continuous rotation of the coil in the magnetic field ensures that the magnetic flux through the coil changes continuously. This continuous change in magnetic flux induces a continuous EMF, maintaining the flow of current in the coil. The interaction between the induced current and the magnetic field generates a torque on the armature, which keeps the motor running.
We hope you enjoyed learning about magnetic flux and its potential impact on future research and development. Thank you for watching and exploring this intriguing concept with us.